that we have two 20-minute talks in this session. After that, we'll have a half an hour break. And then after that is the big event of the day, which is the hour talk by our principal speaker, Jessica Purcell. So that's the plan for the rest of the day. And we'll have a similar schedule for each of the next 2 days. Okay, but let's get started again. Our next contributed talk is by Cong from the University of Wisconsin-Milwaukee. And he's going to tell us about cat-zero right-angled Coxeter groups with Menger curve boundary. So take it away, Cong.
Okay, thank you for the organizer. It's my great honor to speak in such a great workshop. Before I talk about my result, I would like to introduce the motivation. It is well known that Karpowicz and Kleiner classification theorem, which states if the boundary is one-dimensional and the group doesn't split over virtually cyclic subgroup, then the boundary of a one-ended hyperbolic group is either a circle or a Sierpinski carpet as figured A below. Here, the Sierpinski space and the Menger curve. So, but this is not true for cat-zero group, which can have uncountably many non-homeomorphic one-dimensional boundaries. So there is a question by Kim Ruani. Is there any non-hyperbolic cat-zero group with a Menger curve boundary? Haulmark, Hruska, and Sathaye in 2020 gave an example. This is the first known example of non-hyperbolic cat-zero group with visual boundary as Menger curve. And in this talk, I'm going to present a new example, use different techniques. My result is the punctured torus admits a triangulation that's a nerve of non-hyperbolic right-angled Coxeter group with a Menger curve boundary. And my technique is based on showing the visual boundary of Davis complex for the punctured torus is a Menger curve. Since this talk, at the end of the talk, I will show you a concrete triangulation. But firstly, I would like to tell you a rough structure of our idea. Also, so firstly, I would like to introduce the definition of Davis complex. So Davis complex, we can build a Davis complex starting from a flag simplicial complex with vertex set. And this gamma is defined by, for each vertex is a generating set. And Vi square equal 1, this is with a relation as this. And Vi, Vj are adjacent. So, and we can create a Q chamber. So for example, this is a triangulation with is our nerve. It's a flag simplicial simplex. Then you cone this nerve. You get a chamber. We call this Q. This is a cone of L. And you can glue a lot of chambers to establish a Davis complex. Of course, I don't think I have time to explain the details. How can we glue all the chambers? But I would like to show you a one-dimensional model in the next slide. The relation is gluing chambers according to the group structure. which is related to the triangulation. So for example, this is the Davis complex for a circle. So this circle I triangulate to several sides. This is the simplest model, but it will be helpful for us to imagine a high-dimensional situation. So this is we start from a triangulation of this circle, and this is the vertices. This is the vertices, and for each vertices, we required a square, b square, like c square, e square, d square equal 1. This is the relation, and the relator is a, b, c, d, e. And then the relation is like a, b equal b, a, and for any adjacent, we require this relation. This is our Coxeter group. And you can glue, this is the cone, the nerve is the A, B, C, D, E. This is the triangulation. And this is our cone of this nerve. Cone of this nerve is our chamber, this cube. You can imagine this is our chamber, this cube. And we call this one cube. And then you glue AQ, AEQ, EQ, EDQ, etc. Then you glue all of the chambers. So the whole stuff is a Davis complex for a circle. So I just want to have a rough impression how this Davis complex can be built. And for this one is a Davis complex for punctured circle. So in the punctured circle, the Davis complex, you have to, from the previous picture, you have to remove all of this part. So the shaded part will be removed. And then this is the high dimensional situation, the twice punctured torus. Is a quite schematic picture. The Davis complex for twice punctured torus means that I start from a nerve with this puncture and this puncture removed. Then the Davis complex is, I just use this to represent the Davis complex for torus. But this is not, you can imagine this is not quite irregular. We will remove all of this half space. All of the half space will be removed. And also, you will remove all of this. And this green, this blue half space and the red half space will be infinitely many and the large dense. It's dense. It's an infinitely many. And this will be removed. So this is the Davis complex for twice punctured torus. And this picture is a Davis complex for once punctured torus. So you start from a torus and remove a puncture. And this part will be removed. This one will be removed. The infinitely many. Of course, in this blue half space, this one, the infinitely many also will be removed. This will be removed. So then the yellow part, of this yellow part, of course, including, I have emphasized this part is also included in our Davis complex for once punctured torus. So after we talk about the construction of a Davis complex, we want to explain what does the visual boundary look like. And one of the concept is the Pontryagin surface. The Pontryagin surface, we can construct a Pontryagin surface start from a torus. And you remove a lot of things now balls from a torus, and you glue a lot of tori for each circle. And you remove a lot of sequence of balls for each torus and glue a torus. The resulting space is a Pontryagin surface. We use this UP to represent the Pontryagin surface. And for the Pontryagin ball, you can start from a ball and remove a lot of balls and glue a Pontryagin, glue a lot of tori. Then you get the Pontryagin ball. This is the kind of process to build Pontryagin surface and Pontryagin ball. So here I have emphasized I use n height to represent the torus and n. I use n to represent the punctured torus, one's punctured torus. This is my notation. So we can prove that the visual boundary for the Davis compass associated with the punctured torus, that's boundary infinity un, is P removes a lot of diagonal red Pontryagin balls. I said red means I just want to distinguish the Pontryagin balls. So our goal is to prove this is the Menger curve. So in the visual boundary, the pictures look like this. Here, from a Pontryagin surface, you remove a lot of disjoint, now dense Pontryagin balls. Since we want to prove this is the Menger curve, we had to mention a good theorem. This is very good, very useful for us to prove that our visual boundary is really a Menger curve. Anderson's theorem states that a compact metric space is a Menger curve, provided M is one-dimensional, locally collected, and has no local cut points, and no empty open subset of M is planar. So in this talk, I will only concentrate on two aspects: no local cut points and locally non-planar. The rest of our property could be a plane from a symmetry, or we can borrow some coronary to prove that. So firstly, I would like to talk about no local cut points. The strategy is to prove that point is not a local cut point. We only need to show for any neighborhood of U, there exists the neighborhood V, such that all points V removing P0 can be collected by a path in U. So this is a simple picture is like this. For each P0 is a U, and you can, for any U, you have to find a V. And for any pair of point Q and R, you have to find a path in U to collect them. This path can go beyond the V, but you can't go beyond U. If we can do this, then this point is no local cut point. It's not a local cut point. So, but we can always find a path collecting any pair of points near P0 in the Pontryagin surface. But our target visual boundary is boundary infinity UN is a subspace of a Pontryagin Pontryagin surface. So our strategy is because we can always find a path in the Pontryagin surface, but this is the drawback because this path may go into red Pontryagin balls, like here. This is the purple line, like here. You can see that. So our strategy is to push all this the purple path out of the red Pontryagin balls. So for example, for this one, we can push this to here. And for this one, we can push to here. So after this push, we can have a new path. That's a green path. Now the new path will lie in our visual boundary, the boundary infinity UN. So this is the rough, this is the technique to prove how this path lies in our target visual boundary infinity UN. UN represents the punctured torus. So for the other property, we need to show this in a locally non-planar condition. Locally non-planar means that for any neighborhood of T0, there exists K5. If we can prove this, the K5 is like this. It's a complete graph for 5 points in U. Note that the blue Pontryagin ball are not this. So this claim can be equivalent to saying there exists a K5 in each blue Pontryagin ball. The fact can be illustrated by the figures on the next slides. So let's recall the previous picture. This is the left-hand picture is a Davis complex for twice punctured torus. And the Davis complex is the yellow one, the yellow part. And compare with the left one, the Davis complex for the white punctured torus is the yellow shaded part. Of course, this time you should include all of this in the blue. According to a number in Danielski, in the visual boundary here, there's always a K5 here in the twice punctured torus. And by symmetry, you can always find another K5 because this is the hyperplane. The blue one is a hyperplane. So for each blue half space, the visual boundary of each blue half space, there is a K5 here. There is a K5 here for each one. The K5. The infinite make K5. So in the visual boundary, you can see this is in the Davis complex, and this is a picture in visual boundary. So roughly, there is a this is a Pontryagin surface, and remove a lot of balls, the red Pontryagin balls, and the blue balls contains a lot of red Pontryagin balls. You have to remove, and there is a K5 in each blue balls. Is that all of each blue balls? Because the blue balls, blue Pontryagin balls are dense, and each blue Pontryagin balls containing a K5. So that means we prove that this is locally non-planar. And finally, I would like to show you a concrete triangulation. Is like this. This is the triangulation of a torus, and we remove a puncture here. And for this puncture torus, we establish the Davis complex. And this triangulation, we can prove that the visual boundary for this Davis complex for this puncture torus has no local count point and locally non-planar. Thus, it is the Menger curve. Okay, thank you for your attention.
All right, thank you. Let's open the floor for questions. So I have one question, which I actually know the answer to, but you said earlier that you were going to create a non-hyperbolic cat zero group.
Yeah.
But you didn't actually mention why why the group you produce here is not hyperbolic.
Oh. This is the non-hyperbolic. Because this triangulation is it has squares. Because this triangulation has some squares in some place, like here. I think there should be a squares here. Oh, let me see this picture. This should be a square here. Yeah. Anyway, I think this picture doesn't work.
Okay, well,
I think that the rough answer is that there should be a square. If this is a hyperbolic group, there should be a square, but we can allow that there is a square in our triangulation. So we claim this is a non-hyperbolic group.
okay, if there are other questions, people should just feel free to jump in. Okay, well, if not, let's thank our speakers.